Balancing reactions with additional species. In this video, I'm going to talk to you about how to use what we've learned about half reactions to balance a big redox reaction here. Our basic strategy is we're going to use the half reactions and the balancing of electrons, just like we've been practicing, to predict the coefficients on the compounds that contain the elements that are changing their oxidation number. And then we're going to use our standard approach to balancing, where we look at the actual number of atoms to balance all of the other things in the chemical reaction. It's still going to be a good idea to work with oxygen and hydrogen last, as they appear so frequently throughout the chemical reaction. And we're also, if you look at this specific one, going to leave potassium sorted to the end, because he's in an awful lot of things as well. So let's start by getting our half reactions, hopefully right. And we will look at who is changing, or not half reaction. Well, we're going to look at our oxidation numbers to figure out whose oxidation number is changing, so we can get our half reactions right. So here for our first thing, we have +1 for the potassium, and 2 times negative, or 4 times -2, or -8 for the total oxygens, and we have to get neutral, so we can see this manganese must be +7. Potassium is +1 here. Oxygen is -4. 2 times -2. So this nitrogen, to get neutral, has to be +3. And then this H2SO4 is going to be +1. Each one of those two, so for a total of +2. Oxygen is going to be -8. And the sulfur here, to get those right, is going to be +6. Now over here, for this MnSO4 and manganese, the this is acting as a sulfate, so it's -2. Again, -8 +6. And this manganese then is going to be the thing that's making this neutral at Mn2. So I can immediately get my reduction, Mn +7, going to Mn +2. And now I'm going to keep going here. +2 for my hydrogens, -2 for my oxygens, +1 for my potassium, -6 for my oxygens. And so my nitrogen here is going to be sitting at +5. And again, this SO4 is sticking together here just like it was here and here. So I can treat it as the polyatomic -2. And these guys are +1 each for a total of +2. And so that's done. So I've got my nitrogens as my secondary change in oxidation numbers. So this +7 went to this +2. And this +3 went to this +5. And that is my oxidation, because the oxidation number is getting bigger. Now to make this work, I can again think of balancing the charges. So that would be 2 electrons. Or I can think about, to go from +3 to +5, it must have lost 2 electrons. And similarly, I can think of balancing the charge, or recognizing to neutralize it from +7 to +2, I must have added 5 electrons. So I'm producing 2 electrons, but I need to get 5 electrons, so obviously those don't match. I can go to whatever the lowest common multiple here is. In this case, it'll be 10, which means I'll be multiplying everybody in this reaction by 2, and everybody in this reaction by 5, which means I will get 10 electrons plus 2 Mn +7, and 2 Mn 2+, and 5 N +3, and 5 N +5, and then as a result I'll be making 10 electrons. Now I'm going to go ahead and transfer these coefficients to the corresponding things. Before I do that, actually, I'm going to take a second and I'm going to erase all of this stuff, because I got a lot going on up here. So I got those 2's. And then I got these 5's. So this will be a 5, and this will be a 5. Go back to that. So the half reaction effectively gives me these numbers. They might get multiplied if I need to multiply them for other things, but right now I've got a pretty good count. So now what I'm going to do is I'm going to go and try and balance the rest of these guys. So I need to figure out this coefficient, and this coefficient. Oops, I put my plus there. I moved my plus up over here. Now to do that, I'm going to try to start with the thing that appears as little as possible elsewhere. So right now, I have sulfates and I have hydrogens, and I don't know who to start with. So I'm going to start with my sulfates. I'm going to recognize that I have 2 sulfates here, doing sulfate right now. I have 2 here, and I have 1 here. So I'm going to guess that I need 3 here. Having done my sulfates, I'm going to work on my hydrogens because there aren't that many hydrogens in this particular example. I have 6 hydrogens over here. So now I'm working with hydrogens. I'm going to erase again so it doesn't get confusing. Now working with hydrogen, I have 6 over here, and I only have 2 over here. So I'm going to change this coefficient to a 3 so that I have 6 hydrogens over here. Again, I might have to make these exponents these coefficients get bigger, but right now I'm going to stop having sort of changed everybody, and I'm going to start checking my other 2 elements, the 2 that are going to be the hardest to work with. So I'm going to start with potassium. Here I have 2 potassiums. Here I have 5 potassiums for a total of 7. Here I have 5 potassiums and 2 potassiums for a total of 7. So I'm a little bit lucky here. These already turned out to be balanced. So I'm probably done. I've done everything but oxygen, and oxygen appears in every single thing. So I just need to go through and total my oxygens to make sure that my numbers at the beginning, my numbers before and after the reaction are the same. Here I have 8 oxygens, 2 times 4. Here I have 10 oxygens, 5 times 2. Here I have 12 oxygens, 3 times 4. Here I have 8 oxygens, 3 oxygens, 15 oxygens, and 4. So on this side, I have 8 plus 10 plus 12 is 30 oxygens. On this side, I have 8 plus 3 is 11, plus 15 is 26, plus 4 is 30. So my oxygens are good. I've balanced everybody. Everybody's done. So our basic approach here, use our half reactions to get some answers. What did I do there? There we go. To get some of our answers, transfer those in, and then we just got to go and balance the rest of the species in the chemical reaction using the old-fashioned method, looking at balancing the most uncommon things first and working towards the most common things. An important note here, I was able to recognize that my sulfur's oxidation state was not changing because every time sulfur appears in this reaction, it appears as a sulfate, SO4 2-. So sulfur is one of the atoms that would commonly have a changing oxidation state, but one tip or one clue I can use is if it remains as the same polyatomic all the way through the atom, or all the way through the reaction, then I'm not worried about its oxidation state changing, and I'm not as worried about it, like I'm not going to balance the sulfur and the oxygen there separately. When I go to balance it, I'm going to balance the sulfates before and after the reaction. So that's how I can balance a redox reaction using additional species.